record on this computer. Here we go. Okay. So let's review. Where are we? We have this concept of a power series, which is a function defined as an infinite series starting at n equals 0 going to infinity with some coefficients represented by the sequence Cn multiplied by basically powers of x, but there could be a minus a inside that power function, which shifts, which that minus a, subtracting a from x can be thought of as a horizontal shift by a units. So what that does is it sort of takes this thing called the power series and sort of centers it at a. Centered at a. And the reason it's called centered is because the domain of a power series is always going to be like a minus r to a plus r, where r is the radius of convergence. Possibly finite, 0, positive finite, I should say, possibly positive finite, 0, or infinity. You could have a radius of 0, which would be just convergent at a. You could have a radius of infinity, which would be convergent everywhere. Anyway, so that is this concept we have established of a power series. And then through an example, this example, which is a geometric series with ratio x, in particular, we sort of, based on what we know about geometric series, we were able to say that not only can we say this converges for x within a range of 1, around 0, like from -1 to 1, specifically it converges to this function, right? So so that example introduced the concept that regular old algebraic functions can be like equal to a power series, but only on like the specific domain, right? The specific like interval around the center. So this is called a power series representation for a function, right? Power series representation of the function 1 over 1 minus x on the interval -1 to 1, which is that power series interval of convergence. Outside of that interval, it diverges. So then yesterday we said, all right, if we can do this with one function, can we do it with other functions? And we started finding ways of manipulating that specific example into other functions. And we did indeed find power series representations for a small handful of other functions. But today, we are going to, what we did yesterday was fine, but we don't need to emphasize it very strongly because it was very limited. You may have noticed the types of functions we were able to find power series representations for yesterday was quite limited. So that strategy isn't really going to be our main approach. Okay, we have a much better approach that I'm going to introduce to you today. But there is one important thing from yesterday's class that we do really need to carry forward, and that is this key idea that we can differentiate or integrate power series functions term by term. And the result is a new power series for the derivative or the integral of the original function that we had before. Okay, so that key idea is going to be something we work with today. So we really just need to remember that from yesterday. The one other thing I might want you to remember from yesterday is this one word I introduced, this vocabulary word, analytic, which is a function is called analytic if it has a power series representation centered at almost any point in its domain. And the question we are going, so sort of you can frame today's topic, which is called Taylor series. Taylor and also Maclaurin series, which are kind of just, a Maclaurin series, just sort of a special type of Taylor series. I'm going to put that in parentheses because it's kind of silly that we even have that distinction. They're all Taylor series. But this topic can be framed in the sense, in the sort of in the context of this question: what type of functions are analytic? So, like, how much can we do with power series? What type of functions can we represent with a power series? Okay, so we're going to start by saying, let's just assume we have a function f of x, and let's just assume that it's analytic. So f of x has a power series representation at A, where A is almost any number in its domain. And I keep on this keeps on coming up, like the almost. I am not really planning on going into detail about where it does or doesn't have a power series representation. I feel like that's not really that relevant for this course. I think that you guys might learn more about that in like a mathematical analysis course, but for this semester, we're not really going to be worried about, like, well, where are the points where it might fail? I'm not going to do that. Okay. So this may seem like a weird way to approach this topic, because if we're kind of exploring the question of what functions are analytic, like what can we do with power series, which type of functions can we represent with power series? Well, to flip that around and say, let's pretend we already know the answer to that question, and we have a function and we know we can represent it with a power series. It's like, well, why would we approach it that way? That's not going to help us answer the question of which functions we can represent with power series, because it's sort of like you're starting from the wrong, with the opposite assumption. You're starting, or not the opposite assumption, but starting from the wrong side. You're like starting by assuming you can do the thing you're trying to, starting by assuming you know the answer already. Okay, but the reason we do it this way is because then we can ask the question, well, what should the power series look like? Well, we know it's going to be, our f of x is going to be equal to a sum from 0 to infinity for some sequence Cn times x minus a to the power n, right? But what is this sequence? What should it look like? Well, one thing we know for sure is that we can start here. If we do f of 0, or no, sorry, not f of 0. If we do f of a, that's what I meant to say, then we would have like c0 times a minus a to the power 0 plus c1 a minus a to the power 1 plus c2 a minus a to the power 2, etc. Right? Well, a minus a to the power, a minus a is 0, right? So since that's 0, 0 to the power anything is 0, except for this 0 to the power 0. 0 to the power, all powers of 0 are 0 except for the 0th power itself. Does that make sense what I'm saying there? Like, all of those are equal to 0. That's 0, that's 0. Except this, 0 to the power 0 equals 1. So this whole thing equals C0. What we have here is, this tells us the very first coefficient in the sequence. So like those coefficients for the power series, well, we know the first one, it's f of a. So if you can evaluate f of a, then you can get the first coefficient in the sequence. Okay. Well, that's a place to start. But now, check it out. Here's what we can do next. We got to go to a new page. Already, wow. Probably could have written a lot smaller, but I didn't. That's okay. See, it's the 14th today. It's actually, before I go to the next page, I just want to grab this much of it. And I'm going to sort of copy it in, but keep it in the middle. Okay, so we started here. Now, let's do f prime. Let's take a look at f prime. Remember how I mentioned that it's going to be important. It's going to be important that we can do a derivative. So if you do a derivative of this here, right? You would bring this n down, right? So we're going to do like cn times n, and then x minus a to the power n minus 1. And actually, we want to start this a little bit higher. We want to start that at 1 instead of 0, because the derivative of you know what, here, actually, it might be easier, instead of writing it out in summation notation, let's write it out just as with the dot, dot, dot. Let's write it out as C0 plus C1 x minus a plus C2 x minus a squared, etc. Okay. We'll go out to C3 x minus a cubed, dot, dot, dot. Okay, if I do the derivative of this, the derivative of this constant term is 0, right? That's gone. But then I get C1 times the derivative of x minus a. That's just 1. Then I get C2, and then I perform the power rule here. I do times 2x minus a, power 1. Then I've got C3, whatever that is, times 3x minus a squared, and so on. Right, so I did my first derivative. Now, if I evaluate that first derivative at a, similar to how we evaluated the original function at a, and we got zeros everywhere except for one spot. Check it out. So from this, we have C1 equals f prime of a. Now we have another coefficient. Let's do it again. Do another derivative. If I do the second derivative, now the derivative of that constant term is 0. Now I have 2c2 right? This 2c2 here times, 2c2 here times x, the derivative of x minus a. And then over here, I had to bring my power down, right? And so I'll get like 3 times 2 times c3 x minus a. And the next one, just to see what the rest would look like, this would have been like 4c4 x minus a cubed. So now this is going to be plus 4 times 3 c4 x minus a squared. Okay. And again, this was f double prime of x, my bad. That was the second derivative. Now again, we evaluate it at a. Everything is 0. Right? All of those are 0, and all we have left is our constant term. So now C2, not going to be f double prime of a, because we're going to have to divide both sides by 2, right? So it's going to be the second derivative of a, evaluated at a, divided by 2. There's our next coefficient. And this process of taking a derivative of the power series and then evaluating at a and solving for the next coefficient can continue. Let's see what we get for one more case. And then I think we'll be able to discern, we might be able to discern the pattern after one more iteration. So if we look at the third derivative, starting from the second derivative here, we do the derivative of the constant term, that's gone. We get the derivative of this term. The derivative of x minus a is just 1. So we just have this as our new constant term. It's going to be 3 times 2 c3. And then over here, we'll have 4 times 3 times 2 x minus a, and etc. Oh, I forgot my c, my c4. 4 times 3 times 2 c4, and then x minus a, and then plus dot dot dot. So evaluating this at a, we have the 3 times the 2 c3. We just have just that constant term again. So divide by 3 and divide by 2, right? And we have our next coefficient, f triple prime at a divided by 3 times 2. And are we starting to see the pattern? Let's zoom out. We're already pretty zoomed out. Are you starting to see what pattern we're having? Question in the chat, what does A stand for? Remember, A is just the center of the power series. So like A is just A is just pretty much any domain element any number in the domain that you want to center your power series at. So we're just, remember, we started this by saying, let's just pretend that we have a function which is analytic, so we can just make a power series for that function centered anywhere in its domain. So like, yesterday we saw some examples, but a lot of them were centered at 0, or like a few of them were centered at 1. We didn't see much variety. But hypothetically, you could have a power series that approximates the function on just a little segment of it, right? A little segment of the curve, just sort of anywhere you want along the curve at whatever x value you choose. And that, so that's what we're sort of thinking about. A represents that center of the power series. Now let's look at the coefficients we found. Here we have C0 is f of a, C1 is f prime of a, C2 is f double prime of a over 2. C3 is the third derivative of f at a over 3 times 2. The next one, I will sort of skip ahead here, would be the fourth derivative of f at a divided by 4 times 3 times 2. So looking at the chat, Hayden has put out a suggestion that the denominator appears to be n factorial. And if you look at what's going on, like here, oops, here, let's kind of keep track of this term. This was the original C3 term. When you take a derivative of that, it gets a 3 factor. When you take another derivative of that, oops, it gets a 2 factor. And so it gets this new factor, it gets a new factor each time. And the factor that it gets each time you take a derivative is the power that it had, right? Because you're just applying the power rule over and over again. But that power keeps going down by 1, right? So if it started at 10, it would have a times 10, and then it would have a times 9, and then it would have a times 8, and then it would have a times 7. And it keeps on going down until you have x minus a to the power 1. And then the next time you differentiate that, the coefficient becomes the new constant term. And that constant term then allows you to solve for that coefficient. So if we want to solve for C10, by the time we get, we're not going to be able to solve for C10 until we've done 10 derivatives. And by the time we get there, we will have applied the power rule 10 times. So we'll have a coefficient with 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. It's factorial. Yeah, that is the pattern. So we'll write the general rule of Cn is the nth derivative of the function evaluated at the center point and then divided by n factorial. All right, so now that we've discerned our general rule for this pattern, we now have a formula for the coefficients of a power series, if that power series exists. Okay, so for a differentiable function, f of x, the Taylor series for f, centered at a number a in its domain, is this. We got, instead of just writing Cn, we can write Fn, the nth derivative of f at a, divided by n factorial, and then times x minus a to the n. That is the formula for the power, for the Taylor series. That's this thing called the Taylor series. And if a equals 0, it is also called a Maclaurin series. So Maclaurin series is just a simple Taylor series where it's centered at 0. It's not really anything special. It's just as like a specific case. I guess it's a special case, but it's not that special because it's not really anything different than a Taylor series. It's just a simple Taylor series centered at 0. That's what a Maclaurin series is. Okay. And there's a couple of results about this. Turns out I'm just going to label this as facts. Here are some facts, which I'm going to present to you right now without proof, but maybe we can talk a little bit more about why these things are true later. Okay. One of the things that's true about power series representations is that they're unique. Which means if a function has a power series representation, then the Taylor series at that point is the power series representation. It's unique, there's only one. And you can build this Taylor series by taking derivatives, right? By taking successive derivatives of the function over and over and over again, right? So, so that is the power series representation because there is only one. And if the Taylor series is a power series representation, it is the power series representation. Okay, so uniqueness means that Taylor series are the gateway to power series representations for functions. So I'll just leave that open. You know, I am going to put a remaining question. How do we know for sure that a Taylor series for F actually converges to F? Spoiler, it does most of the time. But, oops. Oh, crap. It happened. Yeah, but I need that to get small. Well, that didn't work. There we go. That's what I needed to do. I want to address that question a little later. For now, let's practice actually finding some Taylor series. So first off, let's try to find. Oops. Let's find the Taylor series for f of x equals e to the x. Oops. Centered at 0. Okay. Well, this is going to say we're going to do the sum n equals 0 to infinity. We're going to take the nth derivative of e to the x, but then evaluate that at 0. Okay. So we've got to figure out what does the nth derivative of e to the x look like, evaluate that at 0, and then divide by n factorial. Okay, so that's the formula. That's the nth derivative evaluated at a, and then divide by n factorial. And then we will do times x minus 0, because it's a equals 0, to the power n. So this is what it would look like. Okay, so what is the nth derivative of e to the x going to look like? So if f is e to the x, f prime is e to the x as well, isn't it? E to the x is its own derivative. So the second derivative is also e to the x, and so on. The nth derivative is just e to the x. And all of these at 0 are e to the power 0, which is just 1. 1. They're all 1. The nth derivative of the function evaluated at 0 is always going to be e to the 0, which is always 1. So that means this numerator, the nth derivative of the function evaluated at 0, is always going to equal 1. So this is Taylor series is just 1 over n factorial times x to the n, or in other words, x to the n over n factorial. That is the Taylor series. And this equals e to the x. Now, this converges to e to the x. There we go. Now, we actually proved back in section 6.1, when we first started talking about power series, that this particular power series, which I used as an example in that lesson, has a radius, has an infinite radius of convergence. Which means that it converges over all real numbers, right? It's basically the domain of the power series is everything, all x. So if I pull up Desmos over here, and we do that sum from 0 to, we'll start with like 100. 1 over n factorial, let's see which is exclamation point, and then x to the power n. This is a function of x. This is literally a polynomial function, okay? This right here is a polynomial function, but it sure as heck doesn't look like a polynomial function. It looks like an exponential function. If I drop this from 100 back down to 10 or something, okay, that looks more like a polynomial, right? Because it goes up on the left side and it goes up on the right side. 20. Here, let's make it something I can animate. I'm going to put capital N up here, make a slider for capital N, and I'm going to make it go in steps of size 1 from like 1 up to 100. And we can see what this looks like. We're going to go pretty slow here. Even slower than that. Oops. Step of size 1. That's what I wanted to do. There we go. Okay, we're going to bring it back in a little bit. Okay, so now we have a good. So what this is this is a sequence of polynomials. All of these are actually polynomials. Okay, and you know that you can tell they look like they started off looking like quadratics and cubics and 4th degree and 5th degree and so on. But now we're getting degree. The degree of the polynomial keeps on going up. This is the degree: 25 degree, 26 degree, 27 degree. This is the degree of the polynomial, and it's changing very, very subtly over here. Like this, the change is very, very slight on this side. On the left side, you can see it's changing more dramatically as it flips up and down. It's also sort of growing larger and larger. The interval on which it is a good approximation for e to the x is getting bigger and bigger and bigger as the degree grows. And if we zoom in on it now, like this basically just looks like e to the x. Graph y equals e to the x, or I might be able to do that. Maybe not while this is animating. Not while it's calculating power series. There we go. There's e to the x in green. That's the actual e to the x. The red one there is technically a polynomial function, but man, it looks a lot like e to the x, right? And the idea here is that the power series, if you add it up all the way to infinity, it does actually equal e to the x. Like, this is one example of this Taylor series is an example of a power series with this infinite radius of convergence. So these two things are straight up equal to each other. E to the x is an infinite polynomial. And that's true at every domain, every point in the domain. So yeah, so what else can we do? Let's do another one. Here's a good exercise. I want you guys to take a minute to find the Taylor series for f of x equals x to the 4th power plus 1/6 x cubed minus 2x squared plus 5. Can you please find the Taylor series for that? You can do it by taking successive derivatives. And we're going to have this centered at Well, let's do it centered at x equals 0. I think that's the easiest way. And then maybe after that, we can try it centered somewhere else. But we'll do it centered at 0 to start. Give that a shot. All right, what have we got here? First thing first, let's take some derivatives. Second derivative. Third derivative. Fourth derivative. Fifth derivative. And then sixth derivative and onward. It's going to be 0, 0, 0, 0, 0, 0, 0 forever. Okay, so there's derivatives. You can only take 5 derivatives before you're done, and then you're not done, but so the rest is zeros. So the sequence of derivatives kind of just bottoms out and sort of stops being interesting. So now what we want to do is evaluate these functions and derivatives at 0. So we're going to evaluate them at A in order to figure out the coefficients of this Taylor series. So evaluate this at 0. We have zeros, and then we have a 5, right? So 5 is going to be our C0. You evaluate F prime at 0. And this is over 0 factorial, which is over 1. All right, so that's just 5. F prime over 1 factorial. So that's 1 as well. So this is going to be, plug a 0 into here, you get 0, 0, 0. And this doesn't even have a constant term. So actually that is 0. So that's our C1. That's 0. Then we evaluate the second derivative at 0 divided by 2 factorial. So this is going to be, this at 0 is going to be -4. So we have -4 over 2. That's -2. That's C2. third derivative at 0 divided by 3 factorial is going to be the constant term here, which is 1. 1 divided by 3 factorial, which is 6. So that's C3. And then if we go to the fourth derivative, evaluated at 0 is 24. So we have the fourth derivative at 0 divided by 4 factorial. That's 24 divided by 24. I do believe, isn't 4 factorial also equal to 24? So that's actually just 1, and that's C4. After that, 0 is going to be C5, 0 is C6, ... forever. They're all 0. So our Taylor series is actually not really an infinite series. It's more of a finite series. Okay, let's pick this up here, actually. It's going to be C0, which is 5, plus C1, which is 0, 0x. And then plus C2, which is -2, so that's a negative 2x squared, right? And then plus C3, which is 1/6, so that's 1/6 x cubed. And then plus C4, which is 1 times x to the 4th. And there we go. And then the rest is going to be plus zeros forever, right? All the way out to infinity. What do you notice? What did we learn? There's something very specific we can learn from this. Is there a coincidence here? You guys. It's the same function. Thank you. Yes, it's the same. It's the same function. Same exact thing we started with, right? So this was the function. I gave you a 4th degree polynomial. You do the Taylor series of it, and you get that 4th degree polynomial right back again. It just hands you back the same thing. If it's centered at 0, it definitely hands you back the same thing. If you do a Taylor series centered at any other number, it might look a little bit different, but if you simplify it, it would simplify back to the same thing. A Taylor series for a polynomial function always just gives you that polynomial function back again. And so it's not very interesting, because what a Taylor series is doing is it is giving you a successively better and better, like the partial sums of a Taylor series give you better and better polynomial approximations of whatever function you started with. But if you started with a polynomial, the best polynomial approximation is the polynomial itself. And it's not an approximation anymore. It's just equal with a 0 error, right? So yeah, you don't apply Taylor polynomials or Taylor series to regular polynomial functions, because there's no point. We tend to apply Taylor series to, more interesting functions, like transcendental functions like e to the x, sine x, cosine x, those sorts of functions. Okay. I've said there's a term that I've used a few times that you guys need to know. It's Taylor polynomials. These are the partial sums of a Taylor series. Taylor polynomials, partial sums of a Taylor series. Okay. So, if we look at that e to the x one that we looked at for, that we already got, for example, this, 1 over, or actually it's just, 1 over n factorial x to the n, then the Taylor polynomials are denoted with p subscript. So P0 is 1. Well, hang on. Let's write this out. This is like 1 plus x plus a half x squared plus a sixth x cubed plus 1/24 x to the fourth, and then plus like 1 over 120 x to the fifth, etc. So the Taylor polynomials are like 1, and then 1 plus x, oops, 2, and then 1 plus x plus a half x squared, and so on. Plus a sixth x cubed, etc. Okay, that's what I was showing you in Desmos earlier. Interesting question in the chat from Diego there. Can we approximate cosh of x? Yeah, totally. We can. I'd be very interested to find out what that is. So let's review what is the derivative of cosh. Well, first of all, let's do a Taylor series, or let's do a few Taylor polynomials at least. Maybe not the whole Taylor series, because that's kind of hard to find a pattern. But we can at least do some polynomials. Let's just do that real quick. So what's cosh of 0? I believe this is equal to 1, because it's like e to the 0 plus e to the negative 0 over 2. This is just 1 plus 1 over 2 is 1. Derivative of cosh. You guys remember? Is it sinh? Is it just sinh? Just sinh, right? So the derivative of this would be sinh of x. So the derivative at 0 is going to be sinh of 0, which I believe is e to the 0 minus e to the negative 0 over 2. So that's going to be 0. And then the second derivative is back to cosh again. Cosh and sinh just flip-flop back and forth. It's not like sine and cosine where there's this cycling of negatives and stuff. They just flip-flop. That's it. So then we're going to get 1, then we're going to get 0, and then we're going to get 1 and 0, 0 and 1 and 0, and so on, right? So what we get is coefficients of 1, 0x, 1x squared, 0x cubed, 1x to the fourth. But then we also have to divide by 1, divide by 1, divide by 2, divide by 6, divide by 24, etc. And what we actually end up getting is like just the even powered terms of e to the x. So if we go over to Desmos and we do something similar to this, except we just take the even terms, one way to do that is to make this a 2n and this a 2n. Then things change. Here we go. Now we have just the even terms. And okay, I don't even see anything changing. Let's go back to 1. Yeah, they change very slowly. They only change for the first few. You can barely even see the difference. But yeah, after that, it's like, it's so close, it might as well be there. So if this is just the even terms, what do you think you get for sinh? Just the odd terms, which suggests that if you just get even terms for cosh and you just get odd terms for sinh, if you add cosh plus sinh together, what do you get from cosh plus sinh added together? You get the even terms of the e to the x Taylor series plus the odd terms of the e to the x Taylor series. You get all the terms of the e to the x Taylor series. It's just the same as e to the x. So that is like, I mean, you can prove this much easier just using the definitions, but like there is an example of a Taylor series proof that cosh plus sinh equals e to the x. And it's the same kind of proof, by the way, that can be used. That exact same approach is what you can use to show this famous identity. You guys know this identity? Euler's identity, I think it's called. See this one, e to the I pi equals -1. That exact same concept of like adding together Taylor series can be used to prove that. The more general statement is this, that e to the power I theta, sorry, is cosine theta plus I sine theta. That is a more general version of that. And this is proven by adding together the Taylor series for sine and cosine. It's got some complex numbers in it as well, but yeah, that's kind of how it works. Anyway, all right, folks, that's it for this week. See you next time.